like the number of pairings is going to depend on how we choose to label these outside edges. And in fact, it doesn't. This is something that Van Vielen proved in 2000, that the number of alternating sign matrices that correspond to a given pairing, in fact, is invariant under rotation of the labels. This theorem is a special case of a more general conjecture that was just proven this past spring, that the number of alternating sign matrices associated to a given pairing can be interpreted in terms of a decomposition of a certain wave function. They're kind of like Fourier coefficients on a certain decomposition that conjecture that Razumov and Stroganov came up with. And as I said, was proven, not only implies Wieland's theorem, but it also says a lot about methods for calculating these particular numbers. So it was proven by physicists Contini and Sportiello. And now I want to talk about Ilse Fischer's work, because Fischer just recently came up with a much simplified proof of the refined alternating sign matrix conjecture. And so I want to go back to the way Dave Robbins originally counted alternating sign matrices, which is you begin by looking at these monotone triangles. You specify the bottom row of, say, a monotone triangle with bottom row of length 2, say 2, 4, and there are 3 of them. And of course, it's not too hard to figure out how many monotone triangles you can have that sit above a 2, 4 pair. I mean, it's got to be a number that's greater than or equal to 2 and less than or equal to 4 up there. And in general, if the bottom row is K1 and K2, then the number of possibilities is K2 minus K1 plus 1. Well, what if I've got a bottom row of length 3? Let's say the variables are K1, K2, and K3. Is there a nice formula for the number of monotone triangles with bottom row K1, K2, K3? And this is the formula that she came up with. Maybe it's not so nice. But there are a couple of nice things going on here. One is that, in fact, you always wind up with a polynomial in the Ks. It's always going to be, if the bottom row has length n, it's going to always be a polynomial of total degree n choose 2. And in each of the variables, it's a polynomial of degree k minus 1. So that tells us a good deal about this. And as Fischer began to play around with this idea and see if she could find a nice way of expressing these polynomials, well, this is actually a bit of an aside, but of course the number of n by n alternating sign matrices is simply the number. You take this polynomial and you set k1 equal to 1, k2 equals 2, and so on. If you want the counting refined alternating sign matrices, say the ANI, you just take an n minus 1, or bottom row of length n minus 1, and you eliminate I from it. That's what I said about the degrees, and this is the formula that she came up with. So you're looking at a van der Maan product in your variables, and you hit it with this operator. Now the operator is not particularly simple. It's over all pairs p less than q of 1 minus this operator, which simply takes your variable kp and adds 1 to it every place it appears. And then this is a product of 2 of those. So in terms of the operators, this is fairly complex, and yet it gives you something that you can work with. Now, of course, the way to prove this is to use the fact that you know that this is a polynomial. You know it's a polynomial of degree n minus 1 in, say, K1, and show that the left side and the right side agree at n points. But when she had that, she was able to play around with it and come up with a remarkable formula that I don't think anybody had ever observed before about these ANI. these refined numbers of alternating sign matrices, which is that they satisfy this recursion. As you sum over all of them in the row from j equals 1 to n, multiplied by this binomial coefficient times this alternating sign, you get the ith entry in that particular row. And what that tells you is that the a and I are the coefficients of an eigenvector of eigenvalue 1. So once you know this about those coefficients, well, it's an eigenvector with eigenvalue 1. In order to prove that the formula that you've conjectured is correct, all you need to do is verify that the dimension of the eigenspace of the matrix, whose ith jth entry is given by this, that the dimension of the eigenspace is at most 1, and then plug in your conjectured values, verify that they work, and check the constants. That's it. It's done. There's a lot going on behind that, but it's a beautiful, elegant proof that I really like. I want to close, I think I've got 2 minutes left, with some work that a Carleton undergraduate, Nathan Williams, did. Nathan is now a graduate student at the University of Minnesota, but this was 2 years ago. He was doing a senior seminar based on my book. And he was looking at this table, and he started asking questions about it. Actually, I've got the Mathematica code in my book for generating this table as far as you want to generate it, actually counting these numbers. And he asked the question, what if I take an alternating sum of the entries in any row? Well, it's clear that if you've got a row of even length, the alternating sum is going to be 0. But you got a 1, and then a 9. And then you got those numbers. But of course, you get a sequence like this, and the first thing you do is you go to Neil Sloan's encyclopedia, online encyclopedia of integer sequences, and that sequence is there. And what it is the squares of the number of vertically symmetric alternating sign matrices, which is quite interesting. We know the formula for the number of vertically symmetric alternating sign matrices. We know what this formula is. It's fairly easy to verify that in fact is correct. So it's a little tricky. It's a really nice senior paper for an undergraduate to prove that that's correct. It certainly is not a graduate thesis, but it's a nice undergraduate paper to verify that. And that, of course, then raises a conjecture, which I'll throw out for somebody in this room to prove. Is there a bijective proof of this? So if you're looking at vertically symmetric alternating sign matrices, that means that the central column cannot have any zeros in it, because remember that the non-zero entries have to alternate in sign. So if the left and right sides are just reflections of each other, that's going to foul that up. So you can't have any zeros in the central column, which means that the central column must alternate +1, -1, +1, -1, all the way down. And then that means that the entries on to the left of any +1 have got to add to 0, and the entries to the right of any +1 have got to add to 0. And the entries of any, to the right of, to the left of any -1 have to add to +1, and the same thing with those to the right of it. And so what you're actually looking at, if you take the square of the number of vertically symmetric alternating sign matrices, is you're simply taking an alternating sign matrix with a central column that has no zeros in it, and you're filling in the rest any way you want. The left can be anything as long as those row sums are either 0 or +1 alternating. And the right side can be anything that you want as long as you have the correct row sums. And so what his result says is that the number of alternating sign matrices with a 1 in the kth position along the bottom row is equal to the number of alternating sign matrices with a 1 in the kth position where k is even, in the bottom row, plus the number of these alternating sign matrices with no zeros on the central column. And we finessed, is there a bijective proof? Almost certainly a bijective proof would be very difficult if you can find what the match is between these two. But it is interesting that there is some kind of match between those with a 1 in the even position and an odd position. And if you're interested, you can get a PDF file of this talk at that site. Thank you.
And they will be very happy to answer questions in private. Also, let me mention, this is a really beautiful development, but I also have to mention another recent development by Dan Romick and Matan, student Matan, who also has other further formulas.
Yeah, they have a paper, and I apologize for not mentioning this, but they have a paper that looks at the number, not just where you specify what's in the bottom row, but where you specify what's in the 2 bottom rows. So they can extend it slightly in that direction.
Thank you very much. Thanks again.